first speaker is Bowen Shi from Urbana-Champaign, talking about the Entanglement Bootstrap.
Okay, so let me get started. So first of all, it's my great pleasure to be in this institute. And yeah, this is the first time I've been to Cambridge, and the institute is named by Newton, which is the founder of the modern physics. And I'm happy to communicate some aspect of entanglement of the many body systems and make connection to some of your interests, like either category, topological quantum field theory, conformal field theory, and yeah. So either with a mathematical language like category theory, or field theory, you have space-time, always some quantum state, which I will introduce, which is more like a viewpoint of condensed matter physicists, or nowadays it's sometimes called quantum matter, to emphasize the connection with the entanglement of quantum computation and so on. I want to bring as much connection as possible, and I feel like I'm exactly the right person to do this, because I find that when in grad school, I try to understand the literature of category and in field theory, but in the end, I find that, those are so hard to understand. It turns out there is another way to make connections between these, use entanglement. And the goal of today is to give you an overview of the principles and some of the implications and future directions. In fact, this is a research program I have been working on with collaborators, a lot of wonderful collaborators for quite a few years. There are many references I can write down, but let me just write the fusion rule from entanglement, which was done in 2019. Kind of the big paper that opened up the doors. So and there are other things where I will explain on the way. And so about many body system. Okay. So because there are some previous speakers have talked about conformal field theory, so let me start with conformal field theory in 1 + 1D. And that's a good context to introduce the perspective of a many body system. So consider a spin chain. Yeah, a chain of qubit. Each dot, a little circle, represent a quantum bit. So you have two states, spin up and spin down. And in this spin chain, you can write a Hamiltonian, which is the sum of the side j, v of j, v of j + 1. And then you can have a transverse field x with some coefficient. Let's see, it's j. This simple Hamiltonian has a few features. One is that it's local. So like z and the j and j + 1, they are nearby sides. So I can represent the local Hamiltonian terms like a two-body local interaction, and the last term is a single-body interaction. So the Hamiltonian is local. And if you tune to the critical point by tuning the parameter g to some critical value, actually you can take it to be 1, then you get one of our favorite conformal field theory called Ising CFT. And there are very nice properties. Is the smallest minimal model, unitary minimal model with central charge equal to 1/2. And the central charge intuitively is saying that there are low energy mode, it's gapless, and you have left moving mode and right moving mode, and the contribution of them give you some number. And there are primary fields, 1 sigma and psi, and with some nice properties, and there are primary states associated with those operators, and so on. Okay, Yeah, this is one of the most studied models. Well, you have field theory, you have nice category description, and to solve it numerically, take some techniques like tensor network and so on. But now let me tell you something that's less heard about, but actually quite discussed in condensed matter literature. That's the I call it a 1 plus 1D of the E-thing chain. One is a space, another one is a time. And let's think about 2 plus 1D. So quite non-trivial fact is that there exists well, you can push away the left movers and right movers and insert a non-trivial two-dimensional block. So it's like a two-dimensional space. So you have a lattice model filled with qubits. And each of the edge becomes chiral. So the upper edge only carries the left moving mode and the lower edge carries the right moving mode. But if you combine them, you get back the same universal property as the E-thing CFT in one dimension. The bulk is gapped. And so, well, let me put it as a question. So suppose someone knows the 1D E-thing CFT. The question, yeah, let's go back to maybe 20 years and ask the question whether there is a two-dimensional gap system which have chiral edge mode, but the chiral edge modes describe like chiral part of the E-thing CFT. That's not, the answer is not obvious. And you can take other of your favorite one-dimensional CFT conformal field theory. You can ask whether you can insert a bulk to push away the left movers and the right movers, whether you can get a two-dimensional many-body system with equally nice Hamiltonian in the sense that we have considered some local Hamiltonians. So each interaction is local, and take the ground state is effectively the conformal symmetry emerges. That's not an easy question. And in this particular case, is actually the model is found exactly 20 years ago by Kitaev. That Kitaev's honeycomb model is solvable in some sense, and you have a lattice model with spins and near a few size interactions. And if you add a magnetic field in somewhere in the parameter space, you will have a anion theory. Some gap state with non-trivial excitations, anions. In fact, it's in one-to-one correspondence with the three labels, 1 sigma and psi I wrote there. So let me call it anion 1, anion sigma. Just trying to not to confuse the notation. So I call them A1, a sigma, and a psi. So in the bulk is a gap, but you have non-trivial excitations, which I try to explain later. You have non-trivial excitations, and the edge becomes chiral, and the edge becomes like the E-thing conformal field theory in 1 plus 1D. And another, well, let me see, it has anions. And it has chiral central charge. So it's like the difference between the left mover and right mover is now actually equal to a half, because on each edge you only have left mover, not the right mover, and so on. And there is another feature. So I could emphasize in one dimension, tuning to the critical point really needs some tuning. And in fact, you need a Z2 global symmetry to find the critical point. Otherwise, you can easily miss the critical point. But for 2 plus 1D, this model actually is robust under any perturbation. Any local perturbation is okay. Yeah, so that's interesting because you have some very rich physics but the level of many-body state, at least from the condensed matter point of view, don't even have interesting symmetry. So where does this interesting thing come from? Yeah, that's a big theoretical puzzle if you think that way. But from field theory, of course, we all have nice tools to deal with them. But the question is,
So you are saying that the Ising chain can be written in equivalent way.
Yeah. Oh, let me put it this way. So this 1+1D spin chain model needs some tuning of G. You need to tune carefully to get the critical point. But here, you have some local Hamiltonian, even as some perturbation is fine. And how do I relate this to? So you think about a thin slab of the two-dimensional system. And the claim is that if you view as a large length scale, all the universal physics are the same. So it's described by the Ising CFT.
So it's not equivalent, like, Ising CFT, Ising is equivalent to free Fermi using Jordan.
I'm not talking about that equivalence. So here, the two-dimensional model is actually interacting bosonic theory. Yeah. But you're right in some sense. Kitaev tried to solve this model by mapping to some Majorana fermion representation. The Majorana Majorana is coupled to some Z2 gauge field. So yeah, in some sense, you're right.
Way to think about if I'm right is if you bring the edges close to each other, you start removing, making thinner and thinner the bulk, and then the two edges crash on top of each other, then you get the CFT of the Ising model.
Yeah, but C right, C left minus C right minus 1/2.
It's just because they're chiral. So you're adding the two theories, you subtract.
Maybe is a CL equals
0. No, CL minus CR is a half. I am referring to, for example, I guess this is the right moving. So maybe if we are looking at the lower edge, I should have written CR minus CL is a half. Is that what you were thinking? Yeah. Oh, yeah. Yeah, thank you. So maybe let me just write CL is a half. CR is a half, CL is 0. Yeah.
It's just on one.
So the length is not the
It depends on what the picture looks like. If you circle around, but if you look at this,
yes. Right. So the fact that the left molar and the right molar have different central charge actually have a physical consequence, even in equilibrium. So consider finite temperature state. Actually, the temperature should be lower compared to the energy gap. It turns out there is a universal current, energy current, which is I think pi over tau, the chiral central charge CL minus CR times temperature squared. Yeah.
That's chiral, but CFT.
Right. So it depends on how you view it. So suppose you squash the disk into a thin slab like this. Then you have both left mover and right mover, and you treat it as a quasi one-dimensional system. You take your unit cell like this. It's effectively 1D system. Then it becomes non-chiral. It will be effectively, I claim it's the same with the non-chiral CFT.
but so the bulk theory is just like has 3
Yeah, over here you are allowed to talk about anions, and I can make another interesting comment. Suppose you have some non-trivial anion here. anions cannot be created locally, so it actually attach some anion string to the edge, so it actually affects the spectrum of the edge. So yeah, that's some interesting consequence. Well, you can, in this particular example, people seem to know that this corresponds to some primary state of the chiral CFT, so it's quite interesting. Yeah. The chiral icing, yeah. So the double icing have 9. Right. So yeah, it's not the string that is half of it, which is chiral. I think nowadays there should be some other models. I think maybe some due to pattern construction. Maybe later people also find some analytic wave function inspired by CFT correlator. But I'm not completely sure. I can show you some references that may have it.
But Kitai was the first one. Yeah, but they're inspired from Kitai. You can decorate them.
And Kitai said he's inspired by Mo and Reed, so there's a sequence of inspiration. So yeah. No.
It's more like the Haldane model, but with Majorana system. We did that for the calculation for the finite temperature for the Kitai model and verify that.
I see. Good. So let me move on. Yeah, thanks for the next discussions. You mean CFT?
Yeah. Well, that's what through using the sandwich.
What's in the bulk of the sandwich? Topological order.
In general, like Chen-Simon. I'm not sure double icing, but discussion of Chen-Simon.
If you are talking about formulation in field theory, in the continuum field theory, then I'm sure you are right. Right. Not lattice model. I guess so. I'm not an expert on the field, but Okay, so let me say the following. So this is a hard problem for condensed matter physicists, like trying to identify such models of topological orders, especially with this chiral edge mode. Yeah, like a chiral central charge is non-zero, and finding such model is non-trivial. And yes, like if you really try to find the Hamiltonian, but it's extremely important problem, and it has many applications, like relating to topological quantum field theory, but also for topological quantum computation. If you find any of such systems, it naturally can give rise to good quantum memory and breeding fusion at the gates. We will hear about this afternoon. And let me talk about some way to make progress without touching the hardest question. It turns out there are some interesting way we find recently that can partially understand what's going on based on something in the intermediate length scale. So what I'm drawing is a figure with length scales. So this is a microscopic. It's like you have a lattice, But you have the Hamiltonian terms. Yeah, Hamiltonian terms coupling a few nearby sites. H equal to sum of I, Hi. And in general, the system looks quite messy in the smallest length scale, so it's hard. So we cannot solve the problem brute force using computer because the models are interacting. Really, the Hilbert space grows exponentially with the system size. We need very clever numerical tricks, but still, like many questions we want to answer cannot be solved directly nowadays. And now let's go to some large length scale. So this is a very large length scale. And people expect some quantum field theory. And in the case of context I was discussing, the box should be a topological quantum field theory, more accurately, and on the edge it's related to some version of conformal field theory. So let me put question mark. So condensed matter people expect such beautiful field theory emerges at large length scale. But as I said, it's not a trivial problem. So it's like how to go from here to there. No. Hard problem, although there are beliefs. And there is a very popular word to describe this situation. So we don't know exactly how it works, but there are, a lot of structures, interesting, beautiful structures came out of zooming out. And so when the number of qubits is large, so the popular word is called invergence. Well, you probably heard about it a lot of times in different contexts. Like nowadays we have AI. It's like a lot of neurons coupled to each other. They have emergent consciousness maybe. But in living beings like the human brain, there's definitely emergence of consciousness. It's hard to understand. And in biology, there are some of my other favorite examples, which I'll do it later. But let me first say, we want to make progress in intermediate length scale. What can we do on intermediate length scale? So it's like we have a lot of spins, but we try to coarse grain. Take blocks of spin, putting them in a boxes, in a box, but then you can draw a lot of the box to cover a physical system. I suppose you don't, you're not interested in the details, and yeah, this is the spirit of doing RG. So let me say it's RG. It's like we can ask the following question. Suppose we know some of the properties of the system on this intermediate length scale. And for gap system, we want this length scale to be larger than the correlation length. And the question is, can we solve the puzzle with this new approach? So we change the starting point, but we still want to understand the emergence. Like, can we start from some law with a less structure and try to understand why the beautiful like categorical like the F and R, the Pentagon equation, and anions and the antiparticles, primary state, fusion rules, braiding, how they come from. There are a lot of structures. The mathematical theory is rich, but where it come from in the many-body system? So yeah, entanglement bootstrap, I call it EB for short, is one attempt to go from here to there. And if we succeed, and I think we are on the right track, and a lot of evidence, and then this will be an important problem as well, like how the intermediate length scale things we assume will emerge in microscopic. So we try to break down the hard problem into pieces and then solve them piece by piece.
So you really want to be in an intermediate scale. It's not like you pick up the lattice model at micro scale, apply RG, and then you go to the large scale.
It depends. So if we have exactly solvable model like string net and quantum double, the intermediate length scale is actually exactly the microscopic. So we can actually take the model and try to solve the problem. But many of the interesting models are really messy in the small length scale. So we cannot do it all the time. So that's why we, yeah. Or in some sense, we are going to the continuum limit, but in practice, so especially when we talk about topological theory, it turns out we don't need, like an infinite number of such blocks. We need like a 100 times 100, then we can actually literally do everything. I know it's a subtle point. So suppose we, maybe I need to write down the, yeah. That's a hard question to answer precisely for condensed matter people. No, it's the interacting boson. Yeah, it's the Ising CFT. Well, it's dual to free formula in some sense, but it's an interacting bosonic system. Yeah, I have only a chiral thing. It's a chiral version of the Ising.
So you get both the theory of the bucket and the theory of the edge. So same thing as a Chern-Simons theory has a CFT on the edge.
Yeah, and I guess if I look at your picture over there, it's probably like the bulk lattice length scale and distance between
Right. So this is a lattice length scale. But this one is a some you have many sides, you group them together, and this length scale, L is much larger than the correlation length. Correlation length. Correlation length is the length scale that correlation function. If you compute two-point correlation function, the correlation function decays exponentially. So if you look at the exponent, it's like some distance divided by some number. This is the correlation length. Yeah, that's right. Yeah, that's right. So what can we impose on the lattice model? So it's something in terms of well, we don't have symmetry, as I said, so we don't have a symmetry constraint, right? So what can we do? Yeah, that's a big problem. It turns out we were able to come up with some conditions on entanglement. So let me draw the figure for now without explaining what it is, because I said this is related to entanglement and quantum information. Now I take a break and review some basic notation and concept of quantum information. That's my plan. And then I'll come back to explain those conditions and how we learn from just some conditions on intermediate length scale. Okay, so to be more precise, there are two questions. One is about the bulk, gap the bulk. Two is about the chiral edge. So when I introduce this problem, I try to, give a context that both of the problem appears, but actually there are two problems which can be studied separately. The one is that suppose you put the two-dimensional system on a closed manifold with no boundaries, then you don't have the CFT, you don't see the low energy mode. The effective theory should be just topological quantum field theory. And our theory is the following. We try to take a piece of wave function and look at the wave function. This square, well, it's not the entire system, so we don't see the torus, but it's disk-like, and it looks boring as a quantum memory. But suppose the length scale is much larger than the correlation length. Then we can impose local conditions on each of the local balls. Yeah, the conditions I will tell you later. Well, maybe I'll say a few words now. So like partition each little ball into pieces. This is C and B, C, B, and D. And there's some entropy combination. I think I'll do a much better job explaining this after I give you some definition of quantum state, density matrix, and entanglement entropy. So I'll spend some time on that. But the other problem is on the chiral edge. So near the edge, there will be some different assumption we need to identify to learn why the boundary should be a conformal, has a conformal symmetry. Maybe. Yeah. And that's right. That's right. Yeah. Yeah, that's a excellent question. So if we take any collection of qubits, we can compute the entanglement entropy, compute the density matrix, and so on. So there's a lot of information. But the universal property, suppose we believe the answer in this cheating sheet that we have some of our favorite CFT topological quantum field theory. We know that the universal data is just something we can list within a page or something. And so there are a lot of redundant information. So the hard part of the problem, I would say, rather than saying it's extracting the useful information, is to throw away the irrelevant information. That's why we are doing this.
Where you do numerics, you want a large system to extract the theory. Say, but let's
yeah, actually, I'm wondering whether Frank has a comment because you're an expert on tensor network. You know the different length scale, how it helps, right?
That's your numerics domain. The micro will be if you had some analytic method, you just go and that's why, like, you don't need to do this because the correlation like the zero.
So you don't
Yes.
immediately index the what is what a genetic system like viable, it is actually motivation. And that's why you make sure that you have to go about much longer.
This model that you wrote down, or implicitly wrote down, is kind of fun.
Yeah.
About that, right?
Mm. Okay, so this blackboard, the entire blackboard will be on quantum information. They're really the basic, but the relevant ones are not really a whole lot. So I can actually write here. So you have consider some system on, well, people doing quantum information usually work with finite dimensional Hilbert space, and they usually assume you have a tensor product structure. It is not exactly true for fermion, but with a little bit of a modification, we can do that. But let me stick to the simplest setup, that you have a Hilbert space that's a tensor product of a finite dimensional Hilbert space. Well, you can have more. So you have a tensor product of more things. But let me start with a Q-base, quantum bit. So like HA is spanned by just 0 and 1 on A. And for B, the same thing. So let me write this way. And in such a bipartite system, yeah, it's a partition in two systems. I call it a bipartite system. For bipartite system, if we can consider pure state, right? Pure state in the Hilbert space. Well, there are many choices, like 0, 0, which is by definition 0 on A, tensor with 0 on B. Okay, so similarly, we can talk about 1, 1. Yes, it's the same definition. Those states are unentangled, so they are not entangled. You have something on A tensor with something on B. So in general, unentangled states of the form maybe this the psi AB. I suppose you can write the state as a tensor alpha A on beta B. It's unentangled. But with the principle of quantum superposition, quantum coherence, we can come up with a more interesting state, entangled state. So for instance, I'd like to have a Bell state with some parameter theta. It's like a square root of 2, not important, normalization. 0, 0 plus e to the I theta 1, 1. The quantum mechanics is complex, so I add some complex number. But now, let me talk about the so-called reduced density matrix. Reduced density matrix. So you have a pure state on AB, still the 2 qubits. And then we have 2 boxes. Or if you wish, you have a book with 2 pages. The first page is A, the second page is B. Let's read the first page. What's the information there? It's called the reduced density matrix tracing out B of the state. So let me consider the Bell with theta. The ones we're tracing out B, we find that it's a simple algebra. I think it's a good exercise for everyone not familiar. So we say it's a mixture of 0, 0 and 1, 1. But the point is, okay, when we read the first page, we find something, but we don't see theta. And we can do the same exercise for the second qubit, and we compute rho B. It's the same thing. We don't find theta. So we read the first page, we don't see theta. The second page, we don't see it. So where is theta? That's the experience we don't have every day because our piece of paper only record classical information. But the thing we learn from from quantum mechanics is that sometimes the information, is lies in the correlation between the parties. So we need to look at their correlation. It does not make sense to read just the first page, the second page, and so on. You cannot tell the information that way. And we need to be more clever. So it's time to quantify the entanglement. So entangled state can hide the information in the correlations, and entropy, von Neumann entanglement entropy of a density matrix. So given a density matrix, rho of A, von Neumann entropy is defined like minus trace rho A log rho A. We have a log in it. There are other versions of entropy like Renyi entropy and so on. But the von Neumann entropy has a nice property. Is the following. So if you have a tripartite quantum state, it turns out as computed on AB, entropy on AB, but entropy on BC is always greater or equal to entropy on B plus entropy on ABC. This is known as strong subadditivity. This formula is a pretty simple fact for classical state, but for quantum state, this proof is non-trivial. And some people said that any derivation use strong subadditivity should not be treated as a simple derivation. It may contain some deep insight. Good. So SAB is a shorthand notation for S of rho AB. Yeah, that's right. SABC is the state it comes from. The state is on ABC.
Just in case there is more state outside.
Thank you. A nice way to think about it is that maybe you have a pure state on A, B, C, and D, and you trace out D, then you get some mixed state, density matrix on A, B, C, and then, this is true for every such state. And the last one is that, okay, so we see that strong subadditivity says SAB plus SBC is greater or equal to SB plus ABC. Then one question is, how about we take the equality? The equality gives a very special class of state called quantum Markov state. Well, the name is not important, but if there's equality, it turns out rho ABC is uniquely determined by rho AB and rho BC. In general, this is not true, but for this when strong subadditivity saturates, you can learn the global state from local pieces. Okay, I think that's all I want to cover about quantum information background. Okay. Now we can go back to many-body physics. Any questions? Exactly. I'll talk about this in the next blackboard. Yep. Mm. Yeah, here is a counter example. So the bell stick, if you know row A, so set well, let me call it, instead of A and B, call it A and C, and set B equal to the empty set. And you already see that this is not true, right? So you know row A and row C.
So
Yeah.
in 3+9 systems, we have W states and G states.
Yeah.
Which one satisfies this one?
Let me see.
One of the two. That would be interesting to know.
GHZ.
Satisfying the equality.
None of them, I think.
Okay. So there's another class of states.
Yeah.
Nice to have an example of a 3-qubit state.
No, so the GHZ states, of course, the S is one for every partition. So it's something legit. GHZ state. Then GHZ is the entropy for any subsystem is just one. That's 1 plus 1 is 1.
So it satisfies the GHZ state. All right. Good. Yes.
But the goal will be that A and A is very large, not just one qubit.
That's right. Yeah, just to have an idea.
Oh, thank you. So you are saying, let's consider GHZ state on 4 or more parties, right? Yeah. So when it's spin, then you take this at A, B, and C. Yeah, then I agree. Yeah, thank you. So when I say it doesn't work, I thought GHZ state on A, B, C. Yeah, that one doesn't work. This one works. And greater or equal to 4. Yeah. Good question. So what I mean is there is a recovery channel, the quantum channel, given the knowledge of row AB and row BC. So suppose you have row AB and you design some quantum channel based on row BC, then there's an explicit formula to recover row ABC. It's called Pi's recovery map.
Large system and you have all nearest neighbor parts, schematics, then
Let me take this GHZ state. This is a nice example. So we partition this into A, B, and C. Then you know row AB, and then you do a recovery map from B to BC. You get row ABC, and you can keep doing this. And it's like you try to, based on local information, you can enlarge it, and then you enlarge it based on the information around here. You do it again and again, you get a very long state. Okay.
Looks like it's already determined by row AB. Is the phi determined in C?
Phi from B to BC is determined by row BC. Yeah. So the information of row AB is here, and the information of row BC is there. Right. All right. So now let me go to many body physics. So 2+1D system lattice model. Well, I already said one K-types on Pope. Yeah, this one is chiral, which is harder to understand. But let me go to another model by Kittel, which is easier, the Tori code. Yeah, that one is exactly solvable. But my goal is not to tell you every detail about Kittel's Hanling code. I just want to give a setup, so give an example of state that satisfies some broadly applicable assumptions in the intermediate length scale. I think so suppose we are on the square lattice. Square is not important. Consider a state that is 0. Well, the Hilbert space is on the length, and you have a tensor product Hilbert space. That's why I introduced tensor product in the previous blackboard. The product of qubit in this large Hilbert space, we try to write down a nice wave function. So there's a 2 dimension. So suppose when each qubit is all the qubits are 0, we write a big 0 or write nothing at all. And then we write the next configuration with some square, which means the qubit on this square is spin down. So you have some spin up, or spin up, and plus something with some spin down. This one is all 0. Yeah. Yeah. So yeah, when the convention is that whenever I draw something, that means the qubit on the links are 1. In other places it's 0, and so on. Yeah, thank you. Yeah, so loop condensation with a plus. Yeah, every configuration is +1. It turns out that's the ground state of the Tori code. And well, what may not be immediately obvious from this representation is the entanglement area law. Yeah, so usually I introduce the axiom this way, but today I want to do something different. So let me not start from well. Let me make a story. We'll start with the Ising anion. So this one has anions A of 1, A of sigma, and A of psi. Let me do the following thought experiment. Well, suppose we have some excitation A of sigma, the anion, in some position of the lattice. And then it turns out there was a nice formula in the paper by Vitale and Prescott, 2005. They were saying the entanglement entropy of the state on the disk with the anion with anion 8, let me make it general, minus the entropy of the vacuum is log dA. That's a formula I have been staring at for quite some time when I was a grad student. I tried to understand why this is true, why there's a logarithmic of quantum dimension of the anion shows up. Well, yeah, after a few years, I made some progress, but let's make some comment on this formula. So this formula, first of all, it compares the entropy of two states, so one without anion in the disk. Yeah, the disk of the lattice model, you pick a large disk like this, and with some anions here. The anions, of course, it has string operators. But now one of the disk contains anions, and you have different state. So you need to know both the vacuum state and another excited state. Can we do a better job? So it turns out that we can try to do the following. For example, I now try to do just give the state with anions. Can we come up with something? So one choice is the following. Let me call it C, B, and D. Let's do a combination. So as entropy on BC plus entropy on CD minus that on B minus that on D. So what is this? So if we draw the region, the BC is like this. The anion is here. And CD is like this. And B, what is B? And D is this. So let me just do this on the state with anions, the row with anions, anion. Well, this combination looks clever in the sense that the first two terms sits the anion because it contains the anion. The second two terms, they are away from the anion. Actually, the two states, the state with anion and the ground state, are exactly the same state on B and D up to finite size errors. So yeah, and the center is called C. Yeah.
Inside it can be anyways topological.
So it's any shape, evenly common.
Right. That's right. So the cleverness of this partition is that all the corners appear twice, more than once. Once in the plus, the term with plus sign, you have this corner. And here in some term in the minus sign, you have the same corner. Yeah. So it turns out it doesn't matter. That's the statement. It turns out the answer should be a 2 log dA.
Again, I guess the only assumption is that these systems are much larger than sizes are much larger than.
Yeah, that's right. So the thickness, and I think including the distance of the anion to the boundary, should be several times larger than the correlation length. Okay, and there is another even simpler way to try to solve the problem. C and B. Yeah, so yeah, we can ask how about we do something different. So we have B union C, which is the large ball. And for C is a little one, smaller, but still larger than the correlation length, another ball. And B is the annulus. What do we expect? So if we look at the formula Kitaev-Praskil had, naively we would say, well, the disk, you see the anion, right? This one is the anion. So probably you have 2 log dA. Yeah, I'm adding. So this one contributes log dA. This is another one. Yeah. Yeah. So maybe the annulus don't tell you the entropy contribution, then that's the answer. But it turns out it's incorrect. So it turns out we need to minus 2 log dA from the annulus, and we get 0. Yeah. So actually, that's one way to argue that annulus knows something about the anion. So even if the anion excitation is away from the annulus, it actually knows a lot about the anions. And yeah, Yeah, that's a deep question. I will spend several years in grad school, and I'm going to give you a much better answer. Well, should I say a better answer? It's a better answer in the sense that we take a very different assumption. So that formula, guitar Pascal wrote down, they assume some boundary description related to conformal field theory and some modular transformation of.
He's hiding one onion under his sleeve. Another onion outside.
Right. No, the only thing I want to summarize is that the use CFT in some way and themselves were not satisfied with that assumption. Yeah. On the edge. So if you look at the edge, well, you take a disk in the box, you have a mixed state. The mixed state is argued to be related to some thermal state of a conformal field theory, chiral conformal field theory. That's a good question for them. I believe someone asked the question, they would say, well, we will just kind of argue. Okay, I shouldn't speak for them, but if you find Alexia, yeah, you should ask. Right, right. Okay, now go to entanglement bootstrap axioms. Oh, yeah, we don't require symmetries, no symmetry. Including conformal symmetry, so we don't assume conformal field theory, can we still make the prediction? And also, we want the axioms to be about the ground state, well, about quantum state, but the most fundamental one would be a ground state with no excitations. Yeah, let me say it's the vacuum of the many-body system. Yeah, can we really do that? So the annulus is a big hint. So that on the annulus, it turns out if we have different anions, a bar, you find the state labeled by A reduced to the annulus is a very, very interesting state. Why is it interesting? Because the local, on each local ball, you don't really see any excitations. So if you do a partial trace, yeah, let's see, trace out this part. You have row A here, and it's the same with any B on this. So once you trace out part of the annulus, you no longer see the anion. So the quantum state looks the same, but on the entire annulus, the two states are orthogonal for A not equal to B. Yeah, those are not the axioms, but will be derived as theorems from the axioms. What are the axioms?
Sorry, what is the complete sentence associated about?
The axioms of entanglement bootstrap are conditions on the vacuum state. Right. I take a many-body wave function. Yeah, so this is what I trace out.
Your interpretation that rotating on this smaller space equals rotating on the smaller space, that you could move the string into this gap. Is that okay?
Yeah, that's the intuition. So if you already know anions are associated with deformable string, that's one way to understand the formula. But this will be a theorem in our framework. We don't assume that. So that's.
So here you sort of asserted it somehow. So is it about an axiom?
Yeah.
You're going to show us how to do it.
Right. So I want some axiom that derives this. So the axioms are well, on some quantum state, we call it a reference state. So the axioms are on local balls. So on each ball, the partition is into C and B, and C, B, and D. Yeah, you see this is exactly the same partition I used in the previous board. And I said, if there are anions or even some topological point-like topological defect, some interesting thing will happen. You get 2 log dA, which will be greater or equal to log 2 for non-abelian anions. But for the vacuum, you get 0. Yeah. Yeah. That's right. It's 0. And in realistic system, like the chiral state in the Hannen-Kopp, we should expect approximate 0 and the error decay with the length scale. But for solvable models like string net, we have exact 0.
So when you put a particle inside the annulus or inside the disk, whatever it is, you also because you work with ground state, you need to have another a dual particle at infinity, right?
Yeah. Yeah, there must be another. Yeah. Right. Here I'm talking about the vacuum. So, right. No. So this axiom implies area law. So it's no logarithmic term. It's different from CFT. Well, but that one is more restrictive with the area law for round disks. But here is the topological sense of area law is stronger.
If you have a boson or things like that, then it's a vacuum. It's considered to be empty. Yeah? If the anion is the excitation. Any other axiom you might think? And it will make a difference only if B is larger than 1, which means it's a non-abelian anion. So he's applying here is non-abelian anion. That's the interesting part. Everything else is boring. A fermion or a boson.
So if I am a CFT person, I cannot apply.
You don't have it. Sorry for jumping in.
No. Yeah, it's good. Yeah, it's more about. Mm. Yeah, it's about the book, about the topological quantum field theory. Yeah.
That's also an effect for the boundary. This will be related to this.
Maybe
Right.
it's referring to
No.
Mhm. Mm. Mm.
Book is 3D gap spotlight.
Mm. Okay. Let me continue. I think I have 15 more minutes, so I will try to be less ambitious. But the one important thing I do want to cover, definitely want to cover, is the fact that we can, with those axioms, actually, essentially every sentence you can say about topological orders are at least the universal part of the TQFT should follow from those two axioms. That's the thing we spend years trying to prove, and we're getting there. Very close, I should say. Now I want to. I have no time to explain everything, but let me say some statement in terms of this intuition. Is that you have a set of density matrices on the annulus, which is a simplex. So this is a set of density matrices. Is a simplex. Each extreme point have physical interpretation as different anion types, and so on. So simplex is some generalization of tetrahedron. So depending on how many anions you have on the system, and that you have the right number of extreme points. And not always 4 extreme points, but if you take the toric code, you get exactly 4 extreme points. And those extreme points are orthogonal, and so on. That's not a, well, that's something you can confirm in solvable models, but more importantly, this is a theorem under those two assumptions. It's a deep theorem. I'm not going to prove it today, but that's our definition of the simple object of the category and the anion species. Well, you can ask whether our definition is correct in the sense that you have your own idea of anions, like maybe it's excitation that cannot be created locally. And maybe you can try to ask whether this definition of anion gives rise to the right entropy contribution I told you about. And I claim that every such questions you ask, I will say the answer is yes, just based on the two axioms. And there is a deeper axioms that, well, not axiom, deeper theorem that works for broader context is isomorphism. And for this group of audience, I will say the transportation of topological charges. Topological charges or anion charges. The idea is that you have such convex set. This is a convex set of state. A convex set, well, a convex set of state such that it's locally, well, indistinguishable with the vacuum. So on any disk-like region subsystem, you see no information, so you see exactly the ground state. But the isomorphism theorem says that how about we consider this annulus and someone else consider this annulus? Yeah, so imagine there is a physical background. You move the annulus around, and maybe a third person consider this smaller annulus, do they find the same collection of topological charges? Do they agree with each other? Well, the question, the answer is yes, and it's answered by the isomorphism theorem. So it says that the convex set is isomorphic if the region can be deformed to another. What the deformation, by which I mean we take a local piece of the boundary, we add a local bump or delete a local bump. So that's a topological way to deform regions. And if we are allowed to do it any finite number of times, then we can move the region around. This is an annulus. And we can move it here and move it there. And the convex set has exactly the same structure. In this way, we are able to transport the topological charges to different places and compare them. And note that we did it without using any symmetry. Is this surprising? Yeah. The surprising part is I agree that topological order, you have topological charges. The surprising part is that this sounds like a formulation of topological order that actually works on the manifold system. Now I want to explain it in a way that is less mysterious. Again, how can we transport topological charges with no symmetry constraint? It's not like the node theorem when you write down a Lagrangian with global symmetry, you derive conserved current. Here we have no symmetry, but we have some law of entanglement with the similarity. So I think it's some extreme. This reference state the vacuum is an extremal. Extremal state in some sense. So if we go back to our axioms, the two conditions on the box, C and B, C, B, and D. So I told you about the two entropy conditions. Left-hand side, there's something, and I put 0 on the right-hand side. But one thing I didn't emphasize so far is that for any state, an arbitrary state in the Hilbert space, you always get greater or equal to 0. So suppose you take a hard random state, you have volume law, it's a very large entropy. And if you take a finite correlation length model, if the correlation length is not exactly 0, you get some number, maybe 0.1, 0.01. It's always greater or equal to 0. So the axiom, what the axiom says, is that the vacuum state, the so-called vacuum state in our framework, reaches some minimal of some entropy condition. It's extremal. So it feels like you have, the action principle. Everyone in the room knows about the action principle. So like dx dt, and variation principle give you some equation of motion. And the isomorphism theorem is like some version of this, but it's a quantum version. It's something we can talk about only in the world of quantum mechanics. And yeah, somehow we were lucky enough that we succeeded in deriving such a theorem. And I think I have exactly 6 more minutes. So the strong subjectivity is a true statement. Is a truth for arbitrary quantum state. The axioms are something else. It's a statement on what type of state we would like to call as the vacuum. Hopefully, they are the physical states, or at least the physical states have a representative within a gap space of matter that satisfy our axiom. Then we succeed. The isomorphism theorem. Quantum type of Noether's theorem. Yeah, actually, this observation is already made quite a few years ago, maybe already 10 years ago by Eda Kim in a talk, which he wanted to prove something from the axiom, but there wasn't so easy. But he already observed that if such theorem can be proved, it's a some quantum version of Noether's theorem, well, without assuming symmetry. So it's something looks deep. I like the talk. And now with isomorphism theorem, it says that if everywhere the two conditions hold, then we have a uniform space. We can deform the topological charges from here to there. Everywhere, if our framework is correct, then it should be a uniform sense of a gap space of matter. But then that implies the following. So suppose we have a GQFT topological order. And another topological order, the anion content could be different. They are described by different unitary modular tensor category. Yeah. And then, well, on the left, the axiom should be held on each local ball to be a uniform phase. I'm drawing some system in space, some quantum wave function on the space. On the left, you have axioms held on the little balls. On the right, you have the axiom with no violation. So everywhere you check these two conditions, they are locally checkable. You find 0, 0, so everything looks okay, and you say, oh, this is smooth. But if our framework is correct, there must be something different happens on the domain wall. Otherwise, we won't be able to detect. We will say, oh, those are the same gap surface. That's incorrect. So in fact, there must be some violations on this domain wall. And we can even find new particles on the domain wall by regions near the boundary that give you non-trivial convex set. Same idea. So it's like the domain wall is here. You don't see any information on this thing, but if you have a region of both ends touches the domain wall, it turns out it detects non-trivial things. Yeah, we call it parton, and that there has been several years I was wondering like how the partons fit into the framework of existing categorical literature on gap domain walls. I couldn't really find a sentence to describe the subject. So this year, yeah, actually started last year. We made progress with three wonderful collaborators. Matt is here. Is Matt, Roman, Geico, and Milo Moses. Yeah. So we have a paper on archive which describes some category object. We describe so like within the category framework, what are the things that can describe parton? By answering that question, we believe we have something interesting to say to people interested in category. And how much time do I have? Okay, so maybe let me just mention one final thing. So far, everything I said is about gap state, without saying too much about gapless conformal field theory. And another interesting thing I learned in the past few years when I was in UC San Diego with some exciting progress about the chiral edges. So those axioms are about the gap, the bulk. So they have a nice interpretation in terms of entanglement area law. But on the edge, there will be logarithmic corrections. And if you have chiral edges, you draw a disk touches the edge, the entropy contribution will have logarithmic contribution for the pieces near the boundary, but also have area law piece for the region touches the bulk. So partial A is the length of the entanglement cut. It's a bit more complicated, but it turns out we can find some assumption, not in terms of entropy, but something with a local reduced density matrix. We can certify the edge has conformal, conformal distance, and that's the kind of the first step towards some exciting theory about gapless edge. The first step towards a theory of chiral edges. Yeah. And thank you. The goal of the vacuum. Oh. Right. So I would I would say there are different angles to look at the program. So if you talk to me, I can say a little more. But for this talk, I was trying to say this way. So we have a lattice model. Oh yeah, I think it's good if I redraw the figure with something. So, so the Hamiltonian, the local Hamiltonian terms is in a microscopic, the smallest length scale. And now we have the axioms, entanglement area law, if you wish. Area law is in some intermediate length scale larger than the correlation length. And in the large length scale, we have quantum field theory, including TQFT and CFT. So the goal of entanglement bootstrap is this part, is to go from the area law and understand why the rich structure of the quantum field theory shows up in many body systems. And let me, if this is still sounds abstract, let me make an analog to this thing. So, thank you. By bootstrap, I mean we don't really assume any concrete model. We just take a small set of principles and try to look into constraint. I guess I didn't have time to really show you any constraint other than the strong set of activities that something is greater or equal to 0, which is one of the early steps. So the bootstrap result, okay. Maybe I could say the following. In the 1980s, there's a conformal bootstrap in 1+1D. It started with the BPZ paper. So they start assuming some conformal symmetry, in 1+1D, like the visual algebra and so on. And then they were able to derive the concept of a primary state and the fusion rule and breeding satisfied by the constraint. So the way they solve the minimum model, not writing down exactly this model and that, but showing that with the constraint, that's all you can have. And the spirit behind our approach is similar. We assume some constraint and we ask the question, what theory can survive under those constraints? What's this theory are consistent with the entanglement area law? And then we derive all the fusion rules, breeding statistics, and so on. And even apply to concept with defect.
So just like BBZ found normal models, can you sort of find at least some, but some low rank, like some class reproduce the classification of MTC, some like at least low rank, so no one's classified it overall, at least up to some rank.
Yeah, I think we are getting there. We're very close for that in 2D. But that sounds, people already have prediction that the topological order should be MTC in 2 dimensions. So that reproducing this is indeed part of what we are doing. But it doesn't sound exciting enough. But the next thing is that everything I say, including the axioms, can be generalized into a 3 plus 1D topological order 4 plus 1D and so on. And there are not the category predictions are is that uniquely pinned down, or should I say there's a room for investigation which category is the correct one? But we have an independent approach to think about that. Mm. Mm. Yeah.
I don't see any Lagrange, I don't see any.
I think it's really I think what he's saying is this. Anything not come from lattice model, any first principle, you start somewhere in the microscope or property state wave function. Just using intuition to guess property be satisfied. Similar to the bootstrap. Yeah.
Why you don't call bootstrap for the icing chain? Why you don't do bootstrap for the
because I think icing chain is like a first principle construction. You should everything was determined already from the ground state, although from the lattice model. From his point of view, like the rational CFT, you don't know the construction first. You just guess what this field theory should satisfy what kind of properties. You write down all the properties.
suspectivity of the algebra?
Yeah.
What are the equations? Are the strong solidity, which is not even an equation, it's an inequality.
But that one becomes the equation if you have the state that saturates the strong subjectivity. Yeah.
So the condition is saturating strong solidity.
Yeah. So yeah. Yeah.
In a way, you can polarize in straight point.
Okay, so that is your bootstrap equation.
Yeah. Yeah. I guess I guess so. Yeah. 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 Since I have drawn this, maybe I should explain the analog. So one of my favorite emergence in plant is the Fibonacci sequence. Well, in a pineapple, if you buy a pineapple in the supermarket, or you pick up a pinecone, it turns out if you count the number of lines and crosses all the points, you do it around, rotate the pineapple around, and you count the number, it's almost always one of such numbers. So you have emergent simple rules come from no symmetry constraint, but some local constraint. It's kind of like this. We not such an easy problem to say why that's true, but you do have a mathematical theory. You say, oh, you have fn plus 1 equal to fn plus fn minus 1. Then you can predict everything. But is this the final theory we're looking for? If we're interested in plant, why plant have such numbers, maybe we can still ask more questions and build a theory for that. So that's the flavor of entanglement bootstrap. We already have quantum field theory that can describe the numbers. But what we are doing is something cannot be answered by just using field theory. And it's new and exciting.
Well, the question I have is that if you work with topological order, you work on the state, there is a reason that it's reasonable to believe that this ground state wave function using some way, not necessarily a typological,
Right.
probably recover the properties in the sense that in a low temperature, only ground state matters.
Mm-hmm.
But if you use this argument to apply to gapless space, it doesn't work.
Right. That's what I'm saying. We need some other axioms, but we have some success in finding it. Well. Yeah, even for mixed state, if you know what it means, mixed state, let me say topological mixed state. Yeah, we find some version of the axiom that works for volume loss state with a topological property, and that's a work I did after I moved to UIUC with a student and a professor there, Jung. Yeah, so it came out this year. So it's like once we see that the constraint on intermediate scale can go somewhere, we immediately know that it doesn't work for all the physical contexts. For example, the domain wall breaks the axiom, but the axioms are flexible enough so that we can adapt such axiom to other physical contexts. But with the same spirit, and that's the axiom. The error of the axiom can be computed numerically. Is also a nice feature that connects to numerical work. So I think the answer to your question would be, I try to guess the right axiom for a new physical context. There's some room for success. For chiral edge, we believe. No, it's removing some axiom and add another one. Yeah. Yeah, for the gap domain wall, in fact, we are not adding new axiom. We just relax the axiom in a certain direction.
But my question is perhaps the things that I described seem to suggest that the ground state wave function is perhaps not enough for gapless quantum field theory. Does that mean we only need a new axiom, or pure wave axiom? Probably need a new data.
No, the axioms are still the axiom is about the vacuum. Well, what?
Maybe for gapless
There currently there's no evidence for that, but there's a lot of evidence suggests ground state may be enough.
even for gapless.
Yeah, why would you put even a CFT, the ground state may be the only information? Are all the expectations valid, all the correlations?
Maybe for minimum model, yeah. But gapless, no, all this. but what plane function? What function
in the ground. Take the ground state and then take the temperature in the ground.
So that would be evidence.
Yeah, and another evidence come from this paper, which I like a lot. A grad student in our group was very creative in this work. So from the ground state, they can reconstruct a Hamiltonian, local Hamiltonian, based on the entanglement Hamiltonian. And numerical evidence shows that the ground state of this Hamiltonian is almost exactly this ground state. So it's a parent Hamiltonian. So Hamiltonian knows more than ground state. So if you are not comfortable with the ground state, you can work with the Hamiltonian. But I'm not saying everything is proved. It's some ongoing thought. Right. Yeah. Oh, that's just some personal story. So it's like anyons, with anion we can learn this and that, and can we learn this from the ground state? Yeah, that's the problem I was fascinated for a few years in grad school. And the second example. Yeah. So when I read the simplex theorem, I said there are a collection of states in anions. I told you that the states are orthogonal, but I forgot to answer the question. Thank you for bringing it out. So the part that answers the question is the fact that A minus that of the vacuum is 2 times log dA, which I tried to argue in my first single author paper. From constraint of the strong selectivity and so on, and quantum Markov state, and some structure of the information convex set. When I wrote the paper, those are not theorems, those are my assumptions. If you look at my paper, there are quite some assumptions, but the goal of the paper is to say that, it can actually go somewhere. And then we will, in the next paper, we'll prove all the things we assume. So we prove everything using those axioms. Yeah, the area law axiom that Isaac had a few years ago, but got stuck at some point. Yeah, and this is actually a very nice thing that was the first bootstrap equation was used. Actually, the equation goes like, sorry that I didn't include this in my talk, but the equation is like, you can merge annuli into a two-hole disk. So this part knows about the fusion coefficient. There has different boundaries. It turns out the entropy conservation, the conservation of entropy gives the equation that dA dB. dA is the only positive solution of this. It turns out combining entropy conservation and the fact that dA is the unique positive solution, I was able to argue that the entropy difference must be this one due to some constraint, not by solving any models. No, not really. Yeah, in the end, it's the area law. It turns out. Okay. So I should say, yeah, the unique positive solution of chi is dA. Well, if NABC had those nice properties. It's general in the following sense. The only requirement on NABC is associativity and a few others. And a 1B and so on. By associativity, I mean, well, it's easier to draw in diagram. Oops. Yeah, it's a set of constraints, but those constraints are also derived under the axiom, so we actually didn't assume it. Oh, yeah, that's one conclusion of the approach. So far I said we take a disk, but in fact the disk has a single boundary. We can complete the boundary to a point, like a one-point compactification in topology. It turns out that the state we construct on the sphere that way satisfies the axiom on the completion point as well. So it's a perfect state on the sphere. So those two are equivalent. Hey.
If you take the view that you use like CFT,
Mm-hmm.
start with this algebra, you still apply these entanglement bootstrap axioms, will it still take up the AI method? Or do you require kind of lattice?
Currently we are working on the lattice and we didn't assume Lorentz symmetry. Yeah. But if you're talking about CFT, we have a CFT version. So if the CFT version of the axiom satisfies, it seems up to now the outcome seems to have the flavor of a continuum Lorentz CFT. But when talking about RG flow, well, the fixed point looks like the continuum Lorentz CFT. But when we talk about RG flow, indeed there is a difference. Because we are working with lattice models, we can have lattice model which don't have a Lorentz description, and the C theorem won't apply. So it's like C can go up. We will test our result in such models. There's some interesting result to be reported. I think after I left UC San Diego, maybe a student, in particular Xiang Li, they may have new result to tell you.
Maybe you want to make a comment. You mentioned that one of the motivation of the program is to start using this bootstrap program to reconstruct the scoping of terms such as modules and syntactic. And you also mentioned the boundary, but
Okay.
I want to say that there is a mathematical, relatively complete mathematical microscopic theory in along with categorical theory.
Is it your work in 2017?
Yeah.
Okay, yeah, I'm reading that. Yeah. So as I said, we just roughly get the starting point to explore. So I agree. There's a lot to develop. For the gap state, we are making really good progress. On the boundary, gapless boundary, we're just getting started.
But gap boundary already done.
Gap the boundary. Yeah, we will have a lot more results. I can tell you later.